Okay, so if you are on page 289 and looking at the actual exploration, let's see what we've done so far. It says, using only vertical line segments, draw the area. We did. Your shaded region represents a different integral. We got that. And we also renamed the f of x, which is a little f of x at the beginning, to f of t. You're comparing your pictures with others in your group. And we're calling the area under your curve f, and everybody's capital F is different. So now, number 5, we actually did a little bit of this on Friday, I'll put you remember. Recall when we defined the derivative of anything, say f, this is what I want to talk about. We found the derivative of anything, it was the change in the function over the change in x. And as we let this get really, really, really small in a limit, it was df dx with Leibnizian notation. Do you recall that? That's how we defined a derivative. Well, the actual definition is the limit as x goes to infinity of f of x plus h minus f of x over h. But in that limit, this is what we came up with, that we're letting small changes in f per small changes in x is the slope of the line at that point. We okay on that or not? Guys are Monday responsive. Okay. So what I'm going to do is to indicate that little teeny tiny bit, I'm going to draw one more segment right here for mine. You don't have to do this. That one extra segment right there has moved the x that I chose, has moved this over this much. That little tiny space right there, and we're going to call that the change in x. So that my x, the point sitting right above this red one now, is actually x plus dx. Okay, you on that with me on that? Okay. Now, if you were to draw one like that, would your segment be as long as mine? No. Yours, all your segments that you drew, your red segment, if you drew it, would all be different from one another's?
Yeah.
Okay, well, stay with me here. Take a look at this. The number 5 part here is really, really important that you get. It says the change in f in your picture by drawing one more vertical line segment to the right of the last one that you drew in step 2. The change in f, delta f, is the sign, meaning positive or negative, in my case negative. The signed area of your vertical segment. Try that again. Delta f means the change in area by drawing one more. Delta f, that's the change in area. Because the area is all that black stuff. That delta f, that red line right there, is the change in the area per a change in the x. Are you with me? Okay. We're going to represent delta x in your picture by moving x to beneath your new drawn line segment. That small change in delta x is the thickness of your vertical line segment. Yeah? That makes good sense. What is now the height of your vertical line segment? What's the height of this? Little f of x. Little f of x plus delta x, if you want. That's the height of it. Yeah? Okay. Stay with me. It's coming. And then at the very end it says, can you see why Newton and Leibniz concluded that f prime is little f? Maybe you don't. I don't know. But f prime of x, the change in area, it's already got a dx in it. We have already changed it by the width of this thing. But the actual area added right here is f of x. And it's different for all of your graphs. Little f of x I'm talking about. The change in area is dependent upon a dx, which is already in here. Well, it's a small change. And it's dependent more on the height of the next line segment, which is different for all of you. So the change in area, which is what this says, is f at the x that you're at. That the height of that segment determines how much ink it takes to write the next line. You buying that? Mine actually diminished by that because I'm in the negative space right there. So whatever area I had over here, I subtracted this much from it, and I subtracted this much more by adding one more line. So I don't know if you found that to be very exciting or very convincing or whatever, but this is what we've come up with. That the derivative with respect to x of the integral from from a to x of some function is that function evaluated at x. The rate at which the area is changing. That's how you read this. The rate at which whatever follows this derivative, whatever follows this symbol right here, conceptually in your mind by now, you should be able to say the rate at which this is changing at any given moment is the height of the next line segment. That's supposed to be epiphany. It's supposed to be cool. It's supposed to be awesome. I can see some of you are going, I'm going to give you a piece of paper now, and we're going to go through it again in a different way, and perhaps this will help it drive it home that you see how important and critical and cool this is. I hope. You will not be tested on this material on this paper. However, if I were you, I would hang on to it and study it a little bit. It really drives the point home. This is out of a different book, and I like it better, but it still has the same idea in it. This probably doesn't help those of you viewing it, but there's one side of the paper, and here's the other side, and hopefully by the time you actually view this, you will have this paper in your hands so you can follow the discussion. Okay. I want to talk about, since this is the concept we're talking about, I want you to turn the page over. There are two parts of this thing that we're talking about. It's called the fundamental theorem of calculus. There are two parts of it, and the part that we've been discussing is the last half of the second page, where it says, this is the fundamental theorem of calculus, part 1, that follows here. No, that was the conclusion of it. The other part, and it depends on which book you get, whether they call it part 1 or part 2. The important part is that you get both parts. That's it, part 1. Okay, so look at the bottom of that page. It says, underneath the other part, it says this. Go to the right side and keep letting your eyes bounce back and forth from the graph to the ideas that we're doing on the right. It says, let capital F equal the integral from a to x of f of t dt. We've been doing it here. It's a different function now. It's okay. Now think about this. Try to convince yourself of this, and don't nod your head at me until you're convinced. It says, if we let this happen, we're looking at the picture there, then the area of the rectangle shown is f of x plus h, meaning the area out to x plus h, minus the area out to x. That's the area of the rectangle. No?
Where are we?
We're on the bottom of the second page of the paper I just gave. Are your eyes there?
Yes.
All right. I'm going to get rid of this, and I'm going to try to draw that graph up here so that I can point to some things, and hopefully you'll be able to follow on your paper. And if you want to take some notes on your paper, you can. This is an extremely important concept. It's not all that easy to get. So if you don't understand something, don't allow me to go on until you do. It's important, folks. This is really critical. So we've got the graph, looks like this on this paper. Up, down, back up. Going from A to X, which is about here, and out to here. This is an obviously too wide strip, but we have to be able to talk about it. So this is X plus H. This is H right here. And this is the area. Right here, the height of this. Now you got to imagine this thing being super, super, super skinny, drawn right there, maybe the width of my marker. But I have to blow this up so that we can talk about it. I realize that this height and this height are vastly different. We're talking about a strip of something here that's super tiny. I just have to blow it up to talk about it. Are you with me here? So I'm going to call this f of x. This function up here is f of t. And so if this is f of t, this is f of t evaluated at x. You with me? Okay. Capital F of t. I'm sorry, capital F of x as a function of x, just like we did with our, goes from a to x of f of t dt. And this function is the area under the curve. Okay. And this is x, and this is x plus h, a little ways further, but a little tiny ways further. We just have to blow it up to see it. So let me try that one again. The area of this strip that I have shaded right there is capital F of x plus h, means the area from A out to here minus capital F of x, which is the area from A out to here. That's the area of that curve, or the area of that shaded region. Does that make good sense? Remember what capital F is. Capital F is the area. It's a function of x. The area continues to get bigger as we go out farther and farther on the x. And so this right here is a function. It's a function which is area, and the area changes as this changes. And so capital F of x plus h is out to there. That area from here to here, and capital F of x is from here to here. And if I subtract those two, I get the area of the strip. You buy that? Is everybody good with me there? Okay. All right. And we will call that f of x plus h minus f of x. We'll call it h. Why am I calling it h of x? Oh, sure. It's h times f of x. Isn't the area of this, couldn't we also say that it is h, which is that distance right there, times little f of x? Couldn't I say that as well? Okay, so I have two statements for the area of this. One has to do with capital F of x. That would be capital F of x plus h, all the way out to x plus h minus capital F of x. That would be the area of the curve. But that's also, I mean, by direct calculation, would be the width of it times the height, which is h times f of x. We buy that. Okay, so they're both the same. If I divide both sides of this by h, I get this. F of x plus h minus f of x divided by h is equal to little f of x. All I did is divide by h on both sides. You okay with that? That looks familiar. It should, right? Oh, by the way, these are both approximate because we really don't have, I mean, on this thing, even if it's really, really tiny, we really don't have a top, especially right here. We really don't have a top that's straight out. So this is approximate. Okay. So by definition of a derivative, capital F prime of x is the limit. I guess what I'm saying this is if I add something right here, the limit as h goes to 0 of this thingy right here, that's f prime of x, right? If I add this in here, right here, like this, and I let the limit as h goes to 0, we're going to let it get as close to 0 as we want, this gap right here, close to 0 as we want without letting it arrive at 0. What that does by adding the limit is takes this away. It is no longer an approximation. In the limit, it is f of x. Further evidence that f prime, capital F prime, is the function evaluated at x. And the function evaluated at x is the height of that rectangle there. Kind of like we just did with stuff I erased. Just a little more convincing? It is, it should be. Okay? And so that's what it says. It says, therefore, f of x equals the integral of f of t to t implies that the derivative of that, which is the derivative of the integral, is f of x. I think you do. The derivative with respect to x of an integral. These are the two bulwarks of all of calculus. the derivative and the integral. This is the relationship for them. If you find the rate at which the area is changing, it is the function there. It is the value of it's the y value of the function where you are evaluating it. It ties them together. Derivative, integral, all in one deal, and it turns out to be this function right here. It's phenomenal. It's an amazing result, people. It took people centuries and millennia to come up with this.
What do they like? Like, why? Like, how do you use it, and why do you use it, and what's the purpose of using it?
That will take at least the rest of the chapter, probably in the next 2 chapters, to explain fully.
Okay, that's cool, the relationship, I just don't see why.
It is phenomenal.
Maybe just to realize
As they were doing it, the areas they were receiving were just that function evaluated.
No, I want you to go back to, in order to understand the conundrum they had, I want you to go back to the beginning of the chapter, chapter 5. I want to read to you again what they were after and what this chapter is supposed to reveal. So if we go back to the beginning, this was their problem that they had, that they could not solve, not exactly anyway. And so they were hiring groups full of people to find areas of rectangles and add them together. Because that's all they had. They've been using that for a long time. They wished they had something better, that they could get an exact value without so much trouble. And it was a constant struggle and had been for hundreds of years. Listen. In the beginning of chapter 5, page 263, it says, the need to calculate instantaneous rates of change led discoverers of the calculus to an investigation of the slopes of tangent lines, and ultimately to the derivative. We saw that in the limit. Once they had a limit, a concept in the mind of a limit, it all fell together. To what we call differential calculus. But derivatives revealed only half the story. In addition to calculation method called the calculus to describe how functions change at any given instant, they needed a method to describe how those instantaneous changes could accumulate over an interval to produce a function. In other words, they knew that if they had a function and took its derivative, they could find the slope of a line of a tangent line, which means the rate of change at any given moment, any given instant. But what they had now was, for example, they had the velocity of a planet out there in space that they had been tracking. They had velocity of the planet, but they could not tell its position at any given moment because they couldn't get from the velocity back to position. They couldn't get from the derivative back to the original function. They understood that if you took the y-axis times the x-axis of the velocity curve, they understood if you took that it would be the area under the curve, like we did with the freight train. They understood that really, really well. And so they spent all their time finding areas under curves by calculating rectangles, and they only got approximations. They needed a better method for taking a derivative and recovering the function it came from exactly, without approximation, without figuring rectangles. It says that is why they investigated areas under curves, which ultimately led to the second main branch of calculus called integral calculus. Once Newton and Leibniz had the calculus for finding slopes of tangent lines and the calculus for finding areas under curves, one's one-dimensional, one's two-dimensional, they just don't seem to be related. You shade something in, you get area, you tweak a slope until it fits just right. You know that slope. They're geometric operations that seem to have nothing to do with each other. The challenge for them was to prove the connection that they knew intuitively had to be there. The reason they knew it intuitively is because a derivative will give you this one down here, and an integral will take this one and recover this one. There had to be a connection between finding areas and finding slopes. They just didn't know what it was. They knew it had to be there. The challenge for them was to prove the connection. The discovery of this connection, called the fundamental theorem of calculus, brought differential and integral calculus together to become the single most powerful insight mathematicians have ever acquired for understanding how the universe works. That is a bold statement, also a true statement. This is still the leading thing. This relationship between these two guys right here is still the leading thing that allows so much of scientific and engineering work to go on. Now, the reason you aren't so convinced of it is because you've just barely been introduced to it. And so as we go along, it's not going to seem, it's going to be like little sips that you get. It's not like after a workout going and just gulping. I feel so much better. I'm going to give you little sips, and you won't realize that you've been satisfied until I tell you. But knowing what's coming up, You guys, this is the coolest thing. Okay. So I'm gonna erase this, and then we're going to, as Kyle wants to do, he wants to see an example of why it's so cool. And we're going to do one more thing before we do that though, and that is the initial fundamental theorem. I'm sorry, not the initial, the other side of this paper. I haven't seen a more convincing argument for the second part of the fundamental theorem than this. This is the part, this part I'm about to explain to you, is the part that is more important for doing actual engineering work. This, mathematicians find astounding. Engineers are like Kyle, they go, all right, but how do I use it? Okay? And I'm going, it's beautiful, enjoy the beauty. He's going, how do I use it? Okay, I understand that, it's the mindset. I can understand both sides. Okay, so for those of you viewing this, we're on the front side of this, and I hope you have a copy of it. If not, this is what we're studying at least for a few minutes, and I'll show you the other side in a minute. Okay, so this is the useful part. Here we go. It says, let f of x be the integral from a to x of f of t dt. Okay, we've already seen that. If f x is a fixed number, then capital F of x is a fixed number equal to the area of the curve. We'll buy that? That's pretty easy. But if x varies, if x moves around, then f of x is a variable quantity that is dependent on x. Yep. Okay. Therefore, f of x is a function of x. Think of f of x as the area so far. If we let x just move in one direction, we go out like this, we keep letting x go farther and farther and farther out, then we keep adding more and more area. And if we stop right here and take a breather, then f of x, capital F of x is the area so far as we move. Okay? So we see the graph that I just erased, and I wish I hadn't, but I don't, that one had a rectangle in it. Same function. And so we see f of t. You see that axis there? Do you see why it should be called f of t? And we have a t-axis. You see why it should be called a t-axis? Because we're really talking about x being someplace on the x-axis out so far, and f, capital F of x, is how far out. It's the area that refers to the x, not the function. Okay. All right, so consider this. Here's a strange-looking little function. It's got a line to start with, a slanted line, and then a flat line, and then it goes curvy on us. F of x is the area between f of t and the x-axis, which is the area under the curve. Okay, so we're going to consider these one little bit at a time. The very first one there, if I lop that off when x is 1, then I get a triangle, and the area from 0 to 1 is just 1, because 1/2 of 1 times 2 is 1. Did I lose anyone? Okay, next one. Put the next one with it. Then that means that f of 2, capital F of 2, is what we got in the first case, f of 1, capital F of 1, plus the integral from 1 to 2. And the integral from 1 to 2 is 2 because it's a rectangle that is a 1 by 2. And so we have f of 1, which we got to be 1, plus the integral from 1 to 2, which is 2. And so the total area so far is 3. Not hard. Moving on. F of 3 then will be f of 2, which we got in the previous one, plus the integral from 2 to 3. But this one I'm going to have to tell you what it is because it's curvy. We're going to say it's 1.3. And so the f of 3, when we go out to x equals 3, the area so far is 3 plus 1.3 or 4.3. Easy. It's coming, folks. It's coming. Turn it over. Turn the page over. Now we're on this side, people viewing it. We're right up there at the top of that page, continuing on. And so, and you're thinking, oh, I'm going to do this all the way up. Just stay with me. We'll come to you. Just a minute. F of 4 then will be equal to f of 3 plus the integral from 1, or from the integral from 3 to 4 of f of t, which would be 4.3 from the previous page, minus 1.3, because I'm telling you we've got some symmetry going on there, and the integral from 3 to 4 is the same as it was from 2 to 3, only it's negative. And so the integral, or sorry, f, capital F of 4, meaning we let x go out to 4, has an area, not an area, an integral value of 3. All right so far? Now, look down below that. This implies that the integral from 3 to 4 of f of t dt is, that's what did I want to do yet? F of 4, capital F of 4 minus capital F of 3. Think about that. It's the area out to 4 minus the area out to 3. Because, take a look right here, this is important, right here. This equation, you bought that pretty easily. And it was right, you should buy it. If I just bring the f of 3 over here and subtract it, then we find that the integral from 3 to 4 is really capital F of 4 minus capital F of 3, which should make sense geometrically as well. Okay, so now look at the next one. The next one says f of 5, and I'm not going to f of 4 this time. I'm saying f of 5 is the same as f of 3 times the integral from 3 to 5, so I'm making a bigger jump. So I'm going to go from 3 to 5 in my integral, and I'll add that to f of 3, and that will give me what f of 5 is. You agree with that? Have I lost anybody yet? Because I kind of switched gears on that last one there. I went f of 5 is not equal to f of 4 plus an integral. I'm sticking with f of 3. But if I stick with f of 3 and I want f of 5, I've got to go from 3 to 5 and find that area to add on. And if you amend that equation right there and bring the f of 3 over, you get that the integral from 3 to 5 of f of t dt is capital F of 5 minus capital F of 3. You agree? Therefore, for all cases, if you want to find the integral from a to b under some function f of t, then find capital F of b minus capital F of a. That's the useful part of fundamental theorem, because it allows you to find the area under a curve. That is not an approximation. It is exactly correct, because capital F was defined with a limit, which is right down here. It's defined with a limit, and because in the limit, as we let h go to 0, we get an exact value. Capital F of b minus capital F of a will find the area under a curve. What the heck is capital F of b? I'm sorry, what is capital F of x? Well, this is what we said. Capital F of x was equal to the integral from a to b of f of t dt. You're going, doesn't that seem a little bit, doesn't it turn itself around? I mean, you can find the area under this curve from a to b by evaluating capital F of b and subtracting capital F of a, but what the heck's capital F? How do we find that? Well, remember this. Capital F prime of x was little f of x. Then capital F of x is the antiderivative of little f. If you undo this derivative, then you undo this. When I say undo this, I'm saying this is the derivative of something. Capital F is its antiderivative, little f's. All right, Kyle, here comes the actual application. I'll just do something simple here. If I want to know what the area under the curve is from 3 to 7 of x squared dx, then what I need to do is find capital F. This is little f. Capital F, I'm saying f of x is equal to x squared. So capital F of x, according to this, is the antiderivative of this, which is 1/3 x to the third. Would you buy that?
Would there be a plus c on there?
No, not now, because we're finding a definite integral, which means we're not trying to pinpoint where it is anymore, the antiderivative where the function is. We're trying to actually find the area under a curve. And this is the way we write it. Now that we've seen this proof right here, we find capital F of x by anti-deriving little f in the integral, and we evaluate it. That's what there's put a big old long line here. We evaluate it from 3 to 7. And what that means is take 1/3 of 7 cubed and subtract 1/3 of 3 cubed. That's your A, that's your B. F of capital F of, that's your capital F. This is right here. Capital F evaluated at 7, capital F evaluated at 3 will give you the area under this curve from 3 to 7. And it's big because you know how the parabolas go up. They go up really fast after they get past the origin bit. So what is that? By the way, you can put the 1/3 out here.
Take 105. Wait. 316 thirds.
Okay. So now you got something to calculate, right? Yeah, okay. Let's try it on the example that the book has for you to do. Which is, here, the last example before the exercises. Here's what it says. Find the area under curve of sine x from 0 to pi. Did we all agree that was 2?
Yeah.
Let's see if we can prove it. Now that we understand this a little bit. So now my capital F is an integral from 0 to pi of sine x. How will we find the value of this using the information that you just got? What do we have to do?
You have to end that derive sign.
This little guy here's little f of x. We have to antiderive this, right? So capital F of x is equal to negative cosine x. And we will evaluate that from 0 to pi, which means I will take the negative cosine of pi and subtract the negative cosine of 0. What's the cosine of pi, first of all?
-1.
Negative 1. 1. What's the cosine of 0? 1. This is negative 1. This makes it positive 1.
That's 2.
That's pretty sweet.
Amazing. That's what we were using the other day to play around with the sine function, but it actually does work out if you believe all this, and you should, because people have been using it to make and produce things and do work for a long time, over 100 years.
Good for you.
Okay? So the whole notion here, if you want to just do the assignment and you don't really care about how phenomenal this is, that's okay. When you're asked to find the area under a curve, you have to find the antiderivative of what you're integrating. You have to find the antiderivative of that and evaluate it at the top one and the bottom one and subtract them. And that's what the first page and a half of that handout was out to show you, that how you calculate these things.
Okay, so it took mathematicians like hundreds of years to figure that out.
Yeah.
That seems kind of hard to come up with. I'm not gonna lie. It's pretty.
It is pretty, until the idea and concept inside these geniuses' minds of the limit and what it really truly means, they were able to get these things worked out. Once they figured out and that concept of the limit, it could work with it. Okay, I'm done. I'm very, very excited. I always get excited when I get this lecture, but no one else excites with me. If you ever become a math teacher like me, you'll get excited. Your students will sit there like months too. There you go, folks.